Chemical kinetics is a branch of physical chemistry that studies the rates at which chemical reactions occur and the factors that influence these rates. The theory of chemical kinetics helps us understand how different factors, such as temperature, pressure, concentration, and the presence of catalysts, affect the speed and mechanism of chemical reactions. It also provides insight into the underlying molecular processes that drive these reactions, enabling chemists to predict reaction behavior, optimize industrial processes, and develop new materials. At the heart of chemical kinetics is the concept of reaction rate, which refers to the change in the concentration of reactants or products over time. This rate can vary significantly depending on the type of reaction and the conditions under which it takes place. For instance, the rate of a combustion reaction may be much faster than that of a complex biochemical reaction. Understanding these rates is essential for fields ranging from environmental science to pharmaceutical development and materials engineering. One of the fundamental ideas in chemical kinetics is the rate law, which expresses the relationship between the reaction rate and the concentrations of the reactants. The rate law for a given reaction is typically written in the form R equals Ka squared Mb squared N, where R is the reaction rate, K is the rate constant, a proportionality constant, A and B are the concentrations of the reactants, M and N are the reaction order with respect to each reactant. The rate constant K is temperature dependent and reflects the likelihood that a reaction will occur under given conditions. The exponents M and N, known as the order of the reaction with respect to each reactant, are determined experimentally and indicate how the concentration of each reactant affects the reaction rate. Chemical reactions can be classified into different types based on their order of reaction. A reaction of zero order has a rate that is independent of the concentration of the reactant, while a first-order reaction has a rate directly proportional to the concentration of one reactant. A second-order reaction has a rate that is proportional to the square of the concentration of one reactant or to the product of the concentrations of two reactants. One of the key aspects of chemical kinetics is the study of reaction mechanisms, which are the series of elementary steps by which a chemical reaction proceeds. A reaction mechanism describes the step-by-step process by which reactants are transformed into products. Each elementary step involves the breaking and forming of bonds between atoms, and each step has its own rate constant. The overall rate of a reaction is determined by the slowest elementary step, known as the rate-determining step. Understanding the reaction mechanism is crucial for controlling and optimizing reactions. In some cases, a reaction may involve multiple intermediates or products that are formed and consumed in various steps. For example, in the reaction between hydrogen and oxygen to form water, the mechanism involves the formation of reactive intermediates like H2O2, hydrogen peroxide, before the final product, H2O, is formed. Temperature is another important factor that influences reaction rates. According to the Arrhenius equation, the rate constant K is related to temperature, T, by the following equation. K equals A equal frac EART, where minus A is the pre-exponential factor, frequency factor, EA is the activation energy of the reaction, R is the universal gas constant, T is the temperature in Kelvin. The activation energy, EA, represents the energy barrier that must be overcome for the reaction to proceed. A reaction with a high activation energy requires more energy input to start, leading to a slower reaction at a given temperature. Conversely, reactions with lower activation energies are faster. The Arrhenius equation shows that increasing the temperature increases the rate constant, which results in a faster reaction, as more molecules have sufficient energy to overcome the activation energy barrier. Catalysts are substances that increase the rate of a reaction without being consumed in the process. They work by lowering the activation energy of a reaction, making it easier for reactants to convert into products. Catalysts achieve this by providing an alternative reaction pathway with a lower energy barrier. This effect is particularly important in biological systems, where enzymes act as highly specific catalysts to speed up metabolic reactions. In industrial processes, catalysts are used to optimize reaction rates and increase the efficiency of chemical manufacturing. In addition to temperature and catalysts, pressure can also influence reaction rates, particularly for reactions involving gases. For example, in reactions where the volume of gas changes, increasing the pressure can increase the concentration of reactants, which in turn can speed up the reaction. This is because, according to the ideal gas law, increasing pressure leads to an increase in the number of gas molecules per unit volume, which increases the frequency of collisions between reactants. The concept of equilibrium is closely related to chemical kinetics. For reversible reactions, the reaction can reach a point where the forward and reverse reactions occur at the same rate. At this point, the concentrations of reactants and products remain constant, and the system is said to be at dynamic equilibrium. Chemical kinetics helps to understand how long it takes to reach equilibrium and how factors like temperature, pressure, and concentration can affect the equilibrium position. The study of chemical kinetics is not limited to traditional chemical reactions. It also plays a crucial role in fields such as materials science, environmental science, and medicine. In materials science, kinetics explains the formation and degradation of materials. In environmental science, it helps understand the breakdown of pollutants. In medicine, it is used to study drug metabolism and the effectiveness of therapies. In summary, the theory of chemical kinetics provides a framework for understanding the speed, mechanisms, and influencing factors of chemical reactions. By studying reaction rates, rate laws, activation energy, and catalysts, scientists can predict reaction behavior, optimize industrial processes, and develop new technologies. This theory continues to be a vital tool in chemistry and other fields, with applications that impact many aspects of modern life, from medicine to environmental science to industrial manufacturing.